We know when two similar charges are separated by some distance, they repel each other, and that of two dissimilar charges attract each other. From diagram we can observe it. So there is a force of repulsion between similar charges and force of attraction between dissimilar charges. Wait, this force of attraction or repulsion depends on which factors? From diagram you will say, sir, this force depends on the magnitude of the charges and the distance of separation between them. Yes, you are right. But how? But how the force depends on those factors? Well, Coulomb's law of electrostatics will give answer to this big how. So let's go. It states that the electrostatic force of attraction or repulsion between two charged bodies is directly proportional to the product of two charges and inversely proportional to the square of distance between the two charges. Suppose we have two opposite charges labeled as blue and red, separated by distance small r. F red and F blue are the force of attractions produced by them on each other. Here for a while you can just remember that F red and F blue are equal in magnitude, and let's say it commonly F. Now according to Coulomb's law, the electrostatic force is directly proportional to the product of two charges and it is inversely proportional to the square of distance between the charges. Now if we combine these two expressions, we will get, now by multiplying a constant of proportionality, suppose k on right hand side, we can equate both sides. So what is the value of k? Well, it's a constant and its value depends on the medium between the charges. The medium between the charges may be air or vacuum or water, kerosene, oil, and so on. And also k value depends on the system of unit that we have chosen. It may be SI unit or CGS unit. In vacuum or air medium, for SI unit k is equal to 1 by 4 pi epsilon naught, and for CGS unit k is equal to 1. For medium other than vacuum, k is equal to 1 by 4 pi epsilon. Here just remember, epsilon naught is the absolute permittivity of free space and epsilon is the absolute permittivity of the medium. In another video we will discuss more about them. Till now we have discussed about the variation of the force with charges and the distance between them. But what about the direction of this force? To get the direction we have to consider the vector form of the Coulomb's law. Again, let's consider two dissimilar charges q1 and q2. Let F12 vector be the force acting on charge q1 due to charge q2 and F21 be the force acting on charge q2 due to charge q1, and small r be the distance of separation between them. Let's take a coordinate system and we have our observation point at the origin O. Let r1 be the position vector shows the position of q1 with respect to the observation point O, and r2 be the position vector shows the position of q2 with respect to the observation point O. Let r12 be the displacement vector from charge q1 to charge q2. Here, to get the value of r12 vector, that is r2 vector minus r1 vector, we use triangle's law of vector addition. Let's take the triangle. According to the triangle's law, r1 vector plus r12 vector is equal to r2 vector. So we can write like this. By rearranging the equation, we can get r12 vector. Similarly, you can evaluate for displacement vector from q2 to q1, that is r21 vector. Now let's use Coulomb's law to write the force acting on charge q1 due to charge q2, that is F12 is equal to k q1 into q2 divided by r square. As you can see here, we have written the force in magnitude form, but we are considering the vector form. So let's assign a vector sign over the force. Notice here, if the left hand side is a vector quantity, then obviously right hand side will also be a vector quantity. And now what will you do to make the right hand side a vector quantity? Let me remind you, we can write a vector quantity in terms of product of its magnitude and direction. See, we have a magnitude term on right hand side, that is k q1 into q2 divided by r square. So to make this term a vector quantity, we need to multiply a direction with it. However, to become equal, both vectors on left hand side and right hand side must have same direction. So to make you understand, I am going to multiply the direction of force F12 vector on right hand side. Now we have a proper vector form on right hand side. Now from diagram you can observe the force F12 vector and the displacement vector R12 have same direction. So we can simply replace the direction of F12 vector with direction of R12 vector. Let's represent it as R12 cap. Since we know R vector is equal to R vector mod dot R cap, so from this we can find out R cap, that is equal to R vector divided by R vector mod, or we can also write it as R vector divided by R. Let's use this value in the equation. Instead of R12 vector, we can write it in terms of position vectors, that is R2 vector minus R1 vector. Let's assign it equation 1. So finally we get an expression for force F12 vector. Exactly in similar way, we can find the force acting on charge Q2 due to charge Q1. So now it's your turn. Let's go. Hey, have you remembered in the beginning of video I asked you to just remember F red and F blue are equal in magnitude, but I didn't mention the reason behind it. Let's see why. From equation 1 and 2 we have these values. We can write equation 2 as, now observe the highlighted regions. Yes, you are right, they are equal. So we can replace it with F12 vector. As you can see, there is a negative sign in between them. It means force F12 and force F21 are opposite in direction, and if you take modulus on both sides, then F12 and F21 will be equal in magnitude. We can also look the same equation in a different way. Suppose if charge Q2 doing some action on charge Q1 by attracting it with 2 Newton of force, then in return Q1 will also react to this action of Q2. React, it means reaction, right? So reaction is that Q1 will also attract Q2 with same amount of force, that is 2 Newton. However, both forces are same in magnitude, but they are opposite in direction, as you can see in the diagram. This is nothing but the Newton's third law of motion, that is action and reaction are equal and opposite. Exactly in the same way, you can derive the expression for the force of repulsion for similar charges. Let's see. Wait. One thing you should notice here, that the direction of force F12 vector is equal to the direction of displacement vector R21. So we replace the direction of F12 vector with that of R21 vector. Similarly, you can find F21 vector exactly in the same way. Let's go. Now again, from equation 3 and 4, you can show Newton's third law. So this is all about Coulomb's law in electrostatics. Thank you for watching.